Now, whatever the derivation you guys saw was for collisions in one dimension, right? Now we'll try to do the same thing in two dimensions. So what we are doing is an elastic collision in two dimensions. All right. Now look at the figure. So what we have two masses m1 and m2, and then we have velocities u1, v1 and v2. Okay. Now we have two angles theta1 and theta2, right? Now whenever we are trying to do for two dimension, we have to resolve it into components. So this is what we are doing. Okay. Now what we do is, first we take for the initial case and the final case. Okay, that is before the collision, after the collision, and then we'll try to club these two and try to get an equation out of it. Okay. Now what we have is the component of momentum before the collision. Now before the collision will be m1 u1 plus 0, correct? So that will be nothing but m1 u1. That's basically the initial momentum is only for the first particle. So m1 u1 is the initial momentum, correct, or before the collision. Now next is the component of momentum along the x-axis after the collision. Now this is where we have to start resolving. Now when we talk about along the x-axis, we have m1 v1 cos theta 1 plus m2 v2 cos theta 2, correct? Now conservation of momentum along the x-axis, only along the x-axis, that will be m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2, right? Okay, now for x-axis it's done. Try to do the same thing for the y-axis. Now initial component of momentum along the y-axis is what? 0, right? Now we do the same thing for two objects, that is component of momentum of A along the y-axis will be m1 v1 sin theta 1. Now the same thing, that is the component of momentum of B along the y-axis will be minus m2 v2 sin theta 2, correct? Because it's in the negative direction. Now conservation of momentum along the y-axis, that will give you 0 is equal to m1 v1 sin theta 1 minus m2 v2 sin theta 2. Now this is a elastic collision, correct? That means kinetic energy has to be conserved. So we get half m1 u1 square is equal to half m1 v1 square plus half m2 v2 square. Now what we have three formulas now. That is, first one is m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2, and 0 is equal to m1 v1 sin theta 1 minus m2 v2 sin theta 2, and third one, half m1 u1 square is equal to half m1 v1 square plus half m2 v2 square. Now if you look at this, there are four unknowns, v1, v2, theta 1, theta 2, but there are only three equations, correct? So whenever we have four variables and three equations, what we do is, mathematically if you actually try to solve it, it's not possible. So what we do is, we do it experimentally, get one of the values, and then we try to do the mathematical derivation. Okay, now this is what happens in, suppose let's say an elastic collision has happened in two dimensions. Now the best and the most famous example what we can give is whenever a neutron is there in the nuclear reactor, that undergoes elastic collision. Okay, now whenever it undergoes elastic collision, the point is it has to come and hit the uranium atom, right? So what they do is, they keep these moderators which will slow down the neutron. Now once the neutron collides with the moderators, the energy is cut down and it changes the path. Here the initial velocity of the neutron is known. That means we know one of the values, and then we try to calculate mathematically. We first calculate what will be the kinetic energy, what will be the component along the x-axis, the component along the y-axis, the momentum and all those things. Okay, this is the practical application of collision in two dimensions.